In the previous video, we learned how to use stoichiometry to calculate moles of either reactant or product, knowing the moles of another reactant or product. And we used the balanced chemical equations to be doing the calculations. So balanced chemical equations give us the relative amounts of each reactant or product, but they're in terms of moles. However, when we measure any molecules in the laboratory, reactants or products, we have to weigh them. There is no way for us to figure them out in terms of moles directly on a scale. And therefore, we use mass in grams to weigh these reactants or products, so these molecules, instead of moles. Even though we have the balanced chemical equation, however, we cannot start directly with moles when we have to weigh the reactants and products in laboratory scales. But what we do know, what we have learned up to now, is that if I start with the mass of a compound, I can certainly figure out how many moles of that compound I have by using a simple conversion from mass to moles, using the molar mass of that compound that we calculate. Let's take a look. If I start with the mass of the reactant and I want to end up with a mass of product or another reactant, it doesn't need to be a product necessarily, any of the molecules that I start with in a balanced chemical reaction. But if I start with a mass of a reactant from a laboratory scale, I cannot use the conversion factor from the balanced chemical reaction directly, because that only relates moles of one compound to moles of another. To be able to get there, I first must convert the mass of my reactant to moles of my reactant. And I do that by using the molar mass of the reactant in question. And we've learned to do that previously. We calculate the molar mass, figure it out by adding up all the atoms from the periodic table, the mass of each element, and how many we have, and we figure out the molar mass, so the total mass of 1 mole of that compound. Then we convert from mass of the reactant to moles. Once I have the moles of the reactant, then I can go to the balanced chemical equation and use those molar coefficients to go from moles of one to another. Then once I have my moles of product or my moles of the other reactant, the other compound, then I can use the molar mass of my product, the other compound, whatever it might be, to convert back to mass of the product. And then I can go weigh this out on a scale. Here's an example. So if from a previous problem that we did, where we took N2O2 and we wanted to know how much NO2 was made, that was in terms of moles. But now, if I start with 26 grams of N2O2, how many grams of NO2 am I going to make? Note that there is no shortcut. I cannot use this conversion factor, which relates moles of one compound to moles of another, from the balanced chemical reaction directly, because I don't have molar amounts. I'm starting with grams. To convert to moles, though, so going from grams of N2O2 to go to moles of N2O2, I use the molar mass of N2O2, and I can calculate that knowing the mass of nitrogen, and I have 2 of those, and the mass of oxygen, and I have 2 of those. If I add them all together, I should get 60.02 grams for every mole. Since I start out with grams, I divide by the molar mass to give me moles, and this is how many moles of N2O2 I have in 26 grams. Now that I know how many moles of N2O2 I have, I can calculate moles of NO2 by using the 2-to-1 ratio that is given from the balanced chemical reaction. So I have 2 moles of NO2 for every mole of N2O2. Moles of N2O2 will cancel, leaving me with moles of NO2. And that's what I have here. Once I have moles of NO2, I can convert to grams by using now the molar mass of NO2. Note that I cannot use the molar mass of N2O2 because it's a different molecule and I have to use its molar mass, which turns out to be 46.01 grams. Since I'm starting with moles and converting to grams, I multiply by the molar mass. 0.8664 times 46.01 gives me 39.9 grams. Let's try another problem. We have nitrous oxide, known as laughing gas, is used as anesthetic in dentistry, and it's made by heating ammonium nitrate, which decomposes to give you N2O, laughing gas, and water. Calculate the mass of ammonium nitrate that must be heated in order to produce 10 grams of nitrous oxide. So I'm starting with 10 grams and I'm kind of working backwards. I'm starting 10 grams of my product and I want to know how much reactant do I start with, okay, for part A. And then for part B, calculate the corresponding mass of water that is produced in the reaction. Let's take a look. Here's my reaction. Once again, the first thing I need to do is make sure it's balanced. And I have 2 nitrogens, 4 hydrogens, 2 times 2, 4 hydrogens, 3 oxygens, 1 plus 2, 2 times 1 is 2, so 1 plus 2 gives me 3. So it's balanced. My first step, since I'm starting with grams of nitrous oxide, is to convert any amount in grams to convert it to moles. So I take 10 grams of N2O, find the molar mass of N2O, which is 2 times 14.01, because that's 1 nitrogen weighs about that, and 16, 1 oxygen weighs 16, so that the sum of those comes out to about 44.02 grams. 10 grams of nitrous oxide multiplied by 1 mole of N2O, which weighs 44.02 grams. My grams will cancel, leaving me with, so divide 10 by 44.02 to give you 0.227 moles of N2O. Now that I have the moles of N2O, I can figure out how many moles of ammonium nitrate I can start with because I have the balanced chemical reaction that relates moles of one compound to moles of another. Note that it's a 1-to-1 ratio, which tells me that whatever amount I start with for N2O, that's going to be the same amount of ammonium nitrate. But here it is, worked out for you. Start with the moles of N2O, 0.227 moles of N2O multiplied. Here's my conversion factor from the balanced chemical reaction. Moles of ammonium nitrate on top, because that's what I'm calculating. Moles of N2O on the bottom, because I am starting out with moles of N2O. That will cancel, leaving me with 0.227 moles of ammonium nitrate. However, it's asking me to calculate the mass, not the moles of ammonium nitrate. So I have one more step. I can take ammonium nitrate and 0.227 moles that I just calculated and convert to grams by using the molar mass of ammonium nitrate, which is approximately 80.05 grams. Add up the 2 nitrogens plus 3 oxygens plus 4 hydrogens to give you approximately that. If you have forgotten, please work on these and calculate them yourself and then compare them to the numbers that I have here to make sure that you have done them correctly. My moles of ammonium nitrate cancel out, leaving me with grams on top. 0.227 times 80.05 divided by 1 gives me 18.2 grams of ammonium nitrate. So I started out with grams of nitrous oxide and I calculated grams of ammonium nitrate. The first step is using molar mass to go to moles. The second step is using molar relationships from the balanced chemical reaction. The last step is going from moles to grams using the molar mass of my reactant in this case. Let's look at part B. Calculate the corresponding mass of water that is produced in the reaction, starting with the 10.2 grams of nitrous oxide. Oops. Here's my reaction once again, and I started out with 10.2 grams. I already converted that to moles, so it was 0.227 moles of N2O, so I don't need to repeat it. The thing that I need to do now is convert to moles of water. So here's the moles of N2O that we calculated from part A, multiplied by, now I write the molar relationship between these two. I am looking for water, so water is going to go on top, and N2O is going to go at the bottom of that fraction, and then the coefficients are going to go by each molecule. So 2 moles of water up on top, 1 mole of N2O at the bottom. Then the moles of N2O cancel, leaving me with just moles of water. All I have to do is 0.227 times 2 divided by 1, giving me 0.454 moles of water. Now that I have the moles of water, I have one more thing to do to calculate the mass, and that is using the molar mass of water to convert from moles to grams. So I start with the moles of water, 0.454 moles, multiplied by 18.02 grams of water for every mole. Moles of water cancel, leaving me with grams. 0.454 times 18.02 divided by 1 gives me 8.18 grams of water. And now I've also figured out how much water was produced in that reaction. Here's the problem for you to try. What mass of glucose must be metabolized or must react with oxygen in this reaction to produce 175 grams of water? How about CO2? So you're starting out with 175 grams of water. Calculate how much glucose you need to make that much water, and then how much CO2 in grams you're going to need or are going to be made in the same reaction.